Okay, cool. All right, hi everyone again. So this week, just as a reminder, everything to like all the links and the notebooks are online on CU Learn. If you plan on following along, the notebook is there. As always, I'll start off with a few set of slides. This will hopefully give you guys, today we're doing performance metrics, and this will hopefully give you an intuition as to why we want to learn how to compute performance metrics. As I was kind of briefly mentioning to others before this call, the technical side of calculating performance metrics isn't so involved. It's usually just calling a function from a given API. And the functions themselves are like the metrics themselves are pretty easy to implement yourselves. But what's really important is actually understanding what the performance metrics are, what they do, and like basically to understanding what scenarios to use them. So to start off, whoops, I'm on the last of the pages. Let me go to page 1. So just as a disclaimer, as always, these are recorded. So if you have questions, please throw them into the chat. I'll follow along as, or like read from the chat any questions you guys might have. But again, as a reminder, I always encourage you guys to also pose questions out loud if you're comfortable in doing so, whatever format suits you the best. So ML Weekly this week, so like updates from the community. I was only on like 3 kind of major points this past week, but fourth one kind of came across my newsfeed this morning, so I added it pretty quickly. And it's a pretty interesting one. So this week, NeurIPS, the Neural Information Processing Systems, one of the biggest, one of the most eminent machine learning conferences, released its list of papers that were finally accepted to this year's conference. So Google, Stanford, MIT are at the top amongst those. There's some, there's quite a few. So there was a total of almost 2,000 papers accepted this past year compared to about 1,500 last year. Canada, where we sit, is kind of just beneath these like 3 big ML research guns. So like the US obviously is kind of one of the most eminent ones. Hopefully in the future, some of you guys follow from this work, go into research, and hopefully can like contribute a bit more to Canada's numbers in the more applied or technical ML space. This is the one that hit my news feed this morning. So there was this ICLR 2021 paper, another one of the big conferences. This is still undergoing review, but people in the machine learning community are talking about it already as kind of a farewell to convolution. So we don't know who the anonymous authors are because these are going through double blind, but basically transformers that are being talked and debated about and heavily used in natural language processing are now potentially going to be the like go-to method for image type tasks, which is actually a pretty exciting development. There's a lot of people like chatting about this, trying to figure out who the authors are. Like there's a lot of speculation that this is some Google engineers or research team. So JFT, this 300 million data set, is like a Google proprietary data set that they use internally, was one of their methods. You guys can all access the paper. So what's really fun about the machine learning community is they go through this like open review type process. So you can actually see the details of the paper itself. Another hint as to why this might be a Google team working on this is the training time, if I can find it. So the number of TPU days that they required to train their model is 2.5 or like 2,500. So we're talking like, Google level infrastructure to train their model. But anyways, it seems like what they cover is more or less state of the art. And so kind of exciting. You guys are covering convolutions, and we'll talk much more about convolutional neural networks later on in the course. But as like a forewarning, machine learning moves fast. Even LSTMs are now kind of on their way out, given the rise of the transformer. So yeah, in a few years or in even a couple months, it very may be that, the go-to method for image type tasks will in fact be transformers. So yeah, I'd suggest you guys like at least check this out if you want the like latest and greatest in the state of the art. More from a data science, so I'm adding like, in addition to like machine learning level vision type research, I'll add in like data science as well. So plotly visualization is actually something I'll introduce in this tutorial as well. Plotly is just another like graphing library, but the beauty behind it is the interactivity it has with what you plot, and I'll demonstrate that in the notebook as well. And finally, from the NLP field, so there's been a lot of worry by OpenAI, the creators of the GPT-3 model, that people might use it for like nefarious purposes or like overwhelm digital spaces because and as pretending to be basically a human because it has such convincing text generation. So actually this week, a Reddit user, the Gentle Meter, basically was kind of debunked as a GPT-3 bot that started replying on Reddit. Basically, another user recognized some of the things being generated. Like this user was posting kind of at a regularity of like once every minute to post, and some of the things that it was saying were basically were identified as being some of the like training material that GPT-3 was trained on. So yeah, just like an interesting develop, at least within this space, and probably something, so there's like details on the article, but like something that the NLP community on a whole has been kind of keeping an eye out for. It was part of the justification as to why the GPT-3 model was kind of like delayed and staged in its release. So anyways, that's kind of ML Weekly in a nutshell. I had mentioned I had mentioned that the kind of focus of today's tutorial will be more on building an intuition for the different types of performance metrics we might consider, because again, their technical implementation isn't too involved. So what's really key, and I hope that like what you guys take away from this will be a good sense for why we consider all these different metrics and how each might be used in meaningful ways. So really a performance metric is getting to this question of how good is my model? And you can think of metrics as being part of somewhat of a metric zoo. So there exists several dozen evaluation metrics, and it's critical that you pair the right kind of metric to the right problem. So we can kind of like categorize these in a few different ways. So like certain classification type metrics that you might already be familiar with are things like accuracy, precision, recall, specificity, F1 score, the receiver operating characteristic curves, and like areas underneath those. And we also covered in previous tutorials regression type metrics. So basically like measurements of error. So like the mean standard error or mean absolute error, or sorry, mean squared error, or the root mean squared error. They're all kind of like variants on each other. And you might wonder, why do we need so many metrics? And it is because each kind of measures a different thing. And just to also point out, there do exist quite a few other types. So there are like rank aware metrics, statistical type metrics would be things like correlations, computer vision metrics. So like how do you measure how accurately you've like segmented something? There are a few specific to the NLP domain, and others that are kind of like more deep learning related. But today we'll focus basically on the classification type metrics because we've already covered regression types. And hopefully to give you guys like an intuition as to how you can interpret the performance of your model based on the metrics that you measure of it. So to kind of like, as always, build up a sense for what we're doing, assuming we have some arbitrary data set, it doesn't really matter like how high dimensional it is or how big it is. Well, it doesn't matter how big it is, but in a sense, we just have training data. We might build up a trained model on that data, and in combination with whatever our test set is, we'd want to generate prediction scores, right? So of our test set, Here, the color is representing class. The blue ones will be like class 0, negative, and the pinker ones will be like value 1, like class 1. And for each of these, our model should spit out some kind of probability or confidence value that it has for each of those, right? So we hope that a good model will put these blue ones much closer to the 0. So it's confident that it's more likely to be a 0, and put these pinker ones more towards the right, closer to the 1. You can think of this as a probability of, if you want to turn it as a probability, to say the probability that a given sample is class 1. So you want the class 1s to have high probability and the remaining ones to have as close to 0 probability. So that might look something like this. This could be the output of the model, right? So the model is generating kind of this like continuous type value between 0 and 1. And we can see that indeed, we might end up with it having a pretty high confidence on these pink ones, and a lower-ish confidence on these blue ones. And you can tell there are a few of these pinks kind of like interspersed, and this blue one is kind of high as well. And the idea here is we want to know, well, how actually good is this, right? And because our model generated these probabilities, you can kind of look at like the density. This is just like, again, a simulated example, but we can see that the blue, there's like a denser number of samples closer to this blue bit. The pink is a bit higher, although a little like long-tailed, skewed because of this other sample. And the idea here is we want to think of where can we set our decision boundary along this, some kind of threshold that will tell us that the model evaluated at that threshold will achieve a certain amount of performance, right? So like our curves kind of cross here, and we might have some intuition that this might be the best spot for it. But this is also a tunable threshold, right? If I want to say that absolutely everything the model predicts is going to in fact be positive, that would be like taking it all the way down to the 0, or we want to have a very, very stringent threshold. We would say only things with a very, very high probability, we would move that much closer to the 1 and to the right. And so we can actually evaluate this. We can actually see at this decision threshold, how well does our model do? And that's by basically, here we have these like little check marks to say that, yes, this is left of that threshold. So that is what we would call a true negative, right? This is something that the model would call negative, and it is in fact negative. But this pink one, on the other hand, is left of that decision threshold. So this is in fact a false negative, right? So the class is positive, but we falsely call it a negative. And we can do that for kind of like counting each of these samples on this side of the line, but then we can also do it on the other side. In this case, a pink is a positive, and if it's right of this kind of decision threshold, then that would be a true positive. The model does in fact call this correct, as opposed to this blue one, which is a false positive, right? So the class in this case is blue, but we called it a positive. So we can basically tally these up, and it's just a matter of counting. So we have a certain number of samples. In this case, I think there's like 19. So we count the number of times that we get a true negative on this side. So there's like 9 of these check marks, but there are these two samples here, false negatives. And conversely, on the other side, we count the number of times we correctly identified positive. In this case, there's 7, but we do have 1 false positive in this case. So now, if we move, again, that threshold completely to, like, we can vary where this is, and this is continuous space, we can basically reevaluate how our model does evaluated at different threshold values. So if we move it all the way to the right, well, we basically call everything positive, right? So in this case, we do get everything. We get all our true positives, at least with respect to the positive class. We're doing pretty well. But we also incorporate a lot of false positives, right? Literally every blue sample is called a positive, and that may or may not be actually useful to our model. And as for negatives, we get none of them. Like this would be a pretty poor decision threshold, because our model isn't actually doing much better than random evaluated at this point. So we can kind of think of like grouping this like counting process of computing things on different sides of different lines together as part of like a table. So here I've just kind of like swapped the order, but we have like our true positives here, our true negatives, and then these are both your like type 1 and type 2 errors from conventional statistics. And so when we think of like a metric like accuracy, we're just evaluating different kind of rows and columns in combination of this table to come up with what we call a metric. So in this case, accuracy is just like the correct things, the true negatives, the true positives over all samples. So if we calculate accuracy here, we're just grabbing the numbers from this table and adding it into this metric, right? And so in this case, if we just replace, we're going to get 19 or 9 over 19. And so that's about like almost half, like 47%, pretty bad. But if we, again, move this threshold, we can reevaluate accuracy kind of at each point along this space between 0 and 1. And so if we move it closer to that point, we can see that our model, when evaluated at this threshold, we get actually about 84.2%. So there's 16 correct things out of the 19, right? So which ones did we get wrong? We got this one here, this pink one here, and this blue one here. So those are like the 3 that we missed. So now we can kind of, so accuracy is kind of across both classes, but let's say that we're dealing with something that's a bit more like applied. So a typical example is whether this is the result of a diagnostic test for, say, cancer, right? So if like you have, if you are in fact positive and the model says you're positive, there's a much greater weight to the fact that if you get called a positive, there's a lot of downstream consequences that come, like you go to chemo and all these things. Like you really do not want to have many false positives. And where do we get false positives is if that threshold is kind of like not conservative enough. So in this case, we'd want to move it towards the right to have perhaps a higher confidence in our positive class, but also we want a metric that will evaluate perhaps of those predicted positive, how many of those are actually correct. So that then would be something like this. We want to know that everything right of this curve, how many are correct of the 2 possible outcomes, that they are in fact correct and that they have been misidentified, right? So that's, these ones here, the ones that have been missed. So that is basically what we call sensitivity, recall, or the true positive rate. They're all the same type of metric. They just go by different names. And so again, this could tell us how many of the sick patients are correctly predicted. And then there's the converse. We can do the same in the other direction. So another metric that kind of is goes along with sensitivity is specificity. And we want to know of those predicted negative, how many are those correct? So those are all the ones that are the blue class, right? So the blues are these correctly identified check marks, but then it's also including the ones that we miss based on that threshold. And this would give us a sense of how many healthy patients are correctly rejected. So in combination, we can then start plotting performance of our curve over this entire space, right? We can evaluate kind of at each of these thresholds and try and draw out this like trade-off. We're trading off as we move this between 2 things. We can't have perfect sensitivity and specificity as we move this along, but what we can do is we can trace out, all right, sorry, we've got a question. Is the confidence value the confidence of the sample being pink? Yeah, sorry, I guess I had missed this and I hope I clarified that earlier. So like in this case, well, that would be like more of a probability. We can consider this the probability that the class is positive, right? So yeah, so the idea here is we're basically trading off performance depending on where we want to go and based on what we want to prioritize. So as we evaluate at each point within this space, we're going to trace out kind of points along this line or along a line that will draw out in this space. And this star here is the idea that a perfect model will be one that has perfect sensitivity will be maximum here, and then 1 minus specificity. So like the false negative rate is basically 0. So the closer that curve can get to this point here in the plane, the better it will perform. And just as a note, this diagonal is kind of like random. If you were just to randomly guess and generate a model that does no better than just generate random predictions, your curve, as it's evaluated over that space, will roughly follow this line. Like it'll just like jaggedly run along this line. So models get better and better as their curves get closer and closer to, in this case, the receiver operating characteristic, the ROC, this star. And then there's another metric, precision. So here what we're doing, precision is measuring basically of the positive class, how many are correct and how many are, in this case, false, sorry, so this is false, true positive, and a false positive. So these in combination, so here sensitivity, also known as recall, is put onto this lower axis, and then your precision. And so sensitivity and precision in combination really only care about the positive class. And traced out, or like evaluated at different points in this curve, or in this space, will trace out a curve in, so sorry, this is mislabeled, this should be PR curve. But basically trace out a precision recall curve where the best performance will be in this like upper corner here, where both precision and recall are maximized, that have a value of 1. So what that would look like is something like this. And again, this is just like a simulated example, but because we're drawing different points along this curve or within the space, we're basically just creating an evaluation curve for this model in both ROC and also in precision recall. And as an example here, so I highlight this kind of like line as a baseline in the precision recall space because it's kind of like the equivalent of a random, right? So it's basically the proportion of your majority class divided by all samples will kind of trace out this baseline where you basically want models, all your models to do better than that, and hopefully get as close to this point as possible. And as a reminder, again, a perfect, so if you look down at the base here, one way that you can kind of get improved performance is by changing parameters of your model. If you change the parameters of your model in such a way that the probability of your class being positive for all your actual true positive samples is, in this case, much closer to 1, and all those that are negative are closer to 0, you no longer have overlap in the density function of your probabilities for each of these, right? So you would end up with something that looks like this, basically a perfect curve in ROC space and another perfect curve in precision recall space. Again, as a reminder, area under these is simply a way to summarize the performance of your model. Instead of considering an entire curve, you're looking at the area beneath it. So it's a way of kind of collapsing the entire performance in these spaces into a single value. So you can actually compare two different values. So in this case, your area under the ROC curve would be 1, and your area under the PR curve would also be 1. These are animations that have been prepared by someone else, but they're a really phenomenal way to kind of show these intuitions in like a more dynamic manner. So as we're sliding a threshold along that space, that red dot is tracing out where we are along, in this case, the ROC curve, right? So if we call everything a negative, we would be down here. We call everything a positive, we would be up here. And the way that you kind of determine what your actual decision threshold is you'd want to pick a point along here that, again, is closest to 1. The area under this curve is just a static value, so it doesn't matter where you are measuring your performance. Your area under that curve will always be the same, but we can basically measure the trade-off at different points.
Excuse me?
Yep.
Do you mind re-explaining the difference between ROC and PR as metrics?
Yeah, so the ROC, so let me go back, I guess, to here. So ROC is sensitivity and specificity. So if, as a reminder, these two classes are focused on kind of like positives and negatives, right? So sensitivity is true positive rate, and 1 minus specificity is the false positive rate. So we're basically looking at kind of both classes, whereas the precision recall curve really only cares about the positive class, right? So it's evaluated at different points. And I guess as a reminder, I'll just jump back to these metrics here, we're looking across, so here our sensitivity is measured by this row, right? So it's we have true positives in this case, and then we have those that are, I keep mixing up the orders of these because I've swapped the table, but these are false negatives and false positives. And so what we're doing is we're kind of comparing we're trading off between these two metrics in this space, and they only really pertain as to how many of the positive class did we get correct based on combining that class with the two types of errors that they might have, as opposed to the ROC curve, which is only looking at basically the number of things you got correct within the negative class in one case, and the number of times you got something correct in the positive class. It might take a bit of time to kind of like work through the logic, but I'm hoping that in kind of playing around with some of these numbers and these metrics, you'll get a better sense for why we would pick one over the other. And there's a few other animations I'll show that'll hopefully clarify that, if that answers your question. Or
yes, it does. Thank you so much.
Yeah, no worries. So for example, then I guess we'll do this animation anyways, just to give a sense. If our model now, in this case, generates predictions where kind of the density of those points are completely overlapping, as I mentioned before, it kind of traces this curve along this random line. But as your model gets better and gets better at separating those classes, the morphology of the ROC curve will get closer and closer to that perfect point, right? So it's like here they're completely overlapped. We're doing a bit better at separating the positives, a bit better, and we see that the morphology of the curve gets closer and closer to that point. A perfect model, like kind of like the thing that we're going for, will be one that on your test set or evaluation set will achieve that. And that's where you'll see a lot of people comparing their curves. How does their model do compared to a competitor, right? And the closer that you are, and in this case, you also see the increase in AUC. Even as the morphology changes, a single comparative value that we can use is just this like one AUC value that just kind of summarizes how good your model is based on this area under the ROC curve. Similarly, we can then trace the exact same kind of thing, but now let's compare ROC and precision and recall. So in this case, a random model in the PR and ROC space is typically low. So you can see that the ROC value here is along this random, and you can see that the performance never dropped beyond that baseline, the one that I kind of mentioned previously. So when you see this like collapse again, like the minimum performance that a model will have when random will be even a jagged line in that space. But again, we want the PR curve to kind of improve to that point. There are a number of different factors that will influence this. So like this is basically considering like balanced classes, right? So like the size of these two distributions is the same. But then we can also, well, we won't touch onto it just yet, but we can also think of how does your standard deviation of your predictions vary as well. Like it will change these morphologies slightly as well. So here your model's becoming far less, there's far less variation of the model here, even though the like mean and like median statistic of that curve is the same, and that will affect the morphologies of these curves as well in like not the most, in somewhat of a dramatic way, but it's just to get a sense of, again, the intuition as to how you would interpret what the curve that you trace out in this space is based on what your model will be generating. And oops, this I think is the one that will really drive more the point as to why we would want to emphasize so much the ROC curve or the PR curve instead of the ROC curve when we consider class imbalance. So again, these are approximately equal classes. Whoops. And if we animate this, as soon as we drop down that class, like if, so the positive class becomes extremely rare, there's almost no variation in the AUC curve, right? Like it does go down slightly, but the ROC curve is not sensitive at all. And I don't mean sensitive as in terms of like sensitivity, but it's like, it will not change if, regardless of the class imbalance between your data. Like it'll change, but it won't change dramatically. Whereas the PR curve, when we care about the positive class, will actually fall dramatically. So it is much more sensitive and will be used in cases preferentially where there is extreme class imbalance between the two. Then we can, so this I think is just a second. So then to show if the negative class is the one that's that falls, again, the ROC curve will hardly change, if at all. I mean, there's a slight differences in it, but the PR curve basically will like respond to this as well. You can see the baseline, kind of that like tail end point. Once you get to this point, even if you were to call everything a positive, because there's so few negatives, you will have a perfect model, right? A random model, or not a random model, but any model that just calls everything a positive, when the class imbalance is so extreme from negatives to positives, it doesn't really matter what your model is. It will always just call everything a positive and do particularly well. So that's like basically a rise in the baseline to this point of near perfection. So I guess, yeah, that was about half an hour. So then we'll jump now into the actual notebook and kind of like demonstrate some of these. I'm just going to address some of these other questions. So given the static AUC value, are you able to tell if the model is good or does it not give much? Yeah, okay. Yeah, sorry, I guess I answered that. Does anyone have any questions before we jump into the notebooks? Let's give like a couple of seconds here if anyone's like typing anything out. I hope that this was, it's a good way to start like conceptualizing that there are so many metrics that each will kind of address a different thing, and that taken in combination, hopefully it'll help build up an intuition as to how you can interpret your models a bit better. When it comes to actually coding these things, so I guess I'll just jump into, so I'm using Jupyterlab today. So if you have the notebook open, a lot of this is kind of technical in the sense that you just need to come up with a sense of what is your true positive, your true negative, your false positive, your false negative. You guys will likely have seen what confusion matrices are, and that's kind of like the intuition that I built out for them, is how you lay out where your true positives and your type 1 and type 2 errors fall. And then accuracy is kind of just, again, taking the sum of those that are correct and dividing by the sum of all samples together, whether correct or incorrect. So it's just like, it's a measure like holistically of how well you've done, but accuracy is a bit of a dangerous metric when you have such extreme class imbalance, because a model can be made to look really good if there's extreme class imbalance, because the majority class is so large. I'll like touch on this a little bit later, but accuracy to some sense can be a bit misleading, even though broad spectrum, the machine learning community seems to favor it quite a bit. So like we touched on sensitivity and specificity. I've laid out most of their definitions here just because that's kind of when covering performance metrics, you just need to have a sense for how each are calculated. But then when we jump into like actual code, hopefully you'll be able to build out a sense, not only in generating data, building out your models, but hopefully in being able to interpret them hopefully well. So all that we do at the beginning, so I'm just loading up a few things. Here I'm also going to be demonstrating Plotly. So is like an alternative to graphing things. As I had mentioned in like the ML Weekly bit, Plotly is a great way to basically generate interactive type curves. So this is basically the package that I'll use there. I also just like plot a few other things. So I use matplotlib for that as well. And then really it's like, we'll just be creating a few different models and then just generating a few different metrics. So as I said earlier, it's really just a matter of calling these functions. So there's not much else to do when talking about performance metrics, as long as you understand what's going on, when to use them, and then how to call them. So all that I do here, and this, I guess you guys are all becoming quite familiar with the make classification, is just generating 50 or 500 samples so we can get a sense for the size of our data set. I'll just create a logistic regression model. I'll fit it on the data, and then we'll score it. So here, the predict probability is kind of the thing that we care about. That's our confidence in that the sample is in fact positive. So we're just grabbing those for the positive class, those values, and then all we do is, if we want to create an ROC curve, we need the false positive rate, the true positive rate. And if we want to plot this, we need to know kind of like where to draw out each of those points. So this curve, or this function, takes in the true values, the probabilities that you generated, and then just gives you back in a list your false positive rates, true positive rates, all evaluated at each of those thresholds, so that we can trace out these curves. So to visualize this, one thing that I'll do here, just before we do plot some of these things, is show the confusion matrix. So all that we do with respect to that model. So here, the confusion matrix is just taking in the model, your features, the y values, and then we can like plot it in a few different ways. And I'll specify that we're plotting two here. So there's the kind of like raw confusion matrix, which is the actual values, right? So in this case, true negatives and true positives, and then your type 1 and type 2 errors here. But then there's the concept of a normalized confusion matrix, right? So here, instead of plotting out the explicit values, we plot them out instead as proportions. So of the false labels here, we got 90% correct. And then we the true, we get about 89%. So it's just like, it's the same information, just summarized instead as proportions. So basically this is just like code to like throw that together. But yeah, when you're asked to generate a confusion matrix, usually this is the format that you'll traditionally use. So now, when using Plotly, this is a really fun library to work with. So again, analogous to what I had done in the intuition slides, this is kind of the distribution of those values. You can see that these blue ones are typically quite low. The true ones have a typically high value. And this is, so what these things that are popping up here are like interactive labels. So like at each point, I can get a sense for when the predicted score is in the bin 0.05 to 0.07, I guess, there's like 18 samples. And this is interactive, so you can like zoom into different types of parts of the plot. And you can also move around, or whoops, that's auto scale, but you can like pan around. So you can like move some of these things. You can like zoom again into like some of these regions or like bands. Really, it's just like a convenient way to play around with your data a little bit. Can you identify the false positives on the confusion matrix? Yeah, so here, the true label, or I'll do it on this one. The true label, so you want, which one's false positive? So the true label is the positive class, but the prediction was a 0. So this would be your, or sorry, the other way around. So it's false positive is, yeah, class 1, false positive. So sorry. I predicted a 1, but it in fact is a 0. Sorry, this is the false positives. So false positives, false negatives. So a false negative is I predicted that it's a 0 when in fact it's a 1. These are your true positives, and these are your true negatives. It's one thing I'll also point out, be very careful as to how these axes are labeled. Different. So I think at least within scikit-learn, it's consistent, but different types of packages will like vary where the true, like they'll swap these axes sometimes. So you're like, your true label might be here, your predicted label might be here, or the other ways around. And so these will like switch orientations sometimes. Like I've seen also like them go the other direction. By convention, usually it will follow this diagonal. But that's something that you just want to like keep in mind when interpreting them. Make sure just like rationalize through which is the actual class and what is the predicted class, and that will help you basically interpret these. So again, here is the distribution of those probabilities or your confidence scores as an interactive plot. Here, all that I'm planning on doing is, so here what I want to do is I want to show the trade-off between true positive rates and false positive rates at each threshold. So again, we calculated these at each threshold. And then this is just plotting it together on another interactive chart. I print at the top. We're making like a data frame to like collect these things together so we can see what the different like threshold values are. There's like this one erroneous kind of one at the start that's just like beyond 1 to ensure that these fall to 0. But then it's basically in like decreasing order. So I guess it starts at the highest level of confidence and it's just drawing different thresholds throughout and then measuring what the false positive rate is, what the true positive rate is. And then from those, we can plot them in combination. So that gives us something like this. So this will hopefully give you a sense of like the trade-off between the two, or well, it'll show like how each will vary according to the threshold value. And then what we actually, a bit more salient to machine learning is then drawing it as an ROC curve, right? So here your false positive rate is on this x-axis. And so that's also 1 minus specificity. Your true positive rate or your recall or your sensitivity is on this axis. And you can see this model does decently well. And again, this is kind of I think the convenience of maybe doing these with interactive plotting is that if I care to like zoom into a given subregion, I can kind of see where do I want to drop my decision threshold, like kind of the point that would be closest to perhaps 1. I would say maybe my performance is maximized in my model when my decision threshold for the positive class is at this specific point, right? So it's like I'm picking a point along there for my model, but this entire curve, auto scale, this entire curve kind of summarizes its performance as a trade-off between true positive rate and false positive rate. And then similarly, this is for the precision recall curve. Again, there's another function within that just implements calculating at different thresholds your recall values and your precision values. You give it your true labels, you give it your predicted labels. Here for the convenience, I also measure out the baseline. So again, it's just the number of positive samples over the total number of samples. So because it's zeros and ones and my positives are ones, I can just take the sum of those over the number of all. And then here I'm just setting up a few different parameters to plot that. And that gives us this. Traces out, so again, precision and recall on each axis. And this is a decently performant model. I mean, it's hard to tell without something to compare against, but at least compared to random, it does decently well. And to kind of like round out everything, like we can just like measure all the things. Like this has been like a build up to kind of like plotting everything. But when we're talking about metrics, really it's a matter of pulling from the scikit-learn metrics library. So all that I'm doing here is I brought down some of the stuff that we've done before just to make it a bit easier. So I can generate data, I can create a model. So the model up there, I can have it predict on that data. This like metric zoo that I call is literally just like collecting all these functions together into a list so I can iterate over them. And then all I'm doing is just applying, like measuring that metric by passing it in the true label, the predicted label, and then all that I do is plot out. So this is just like a convenient way to like pull out the metrics name. So like each of these and what that value is. And we can generate basically for our model each of these, the accuracy, the precision, the recall. F1 is another way to like kind of summarize the precision recall curve. It's basically the harmonic mean between precision and recall. So if I have no preference over either of these, I weight basically precision and recall together. So F1 is a way to also summarize this plot in addition to area under the PR curve. And another way to summarize this is there's like mean average precision. So it's basically like the average precision value of your like evaluated over the range of recall. So it's like there's a number of, again, different ways that you can extract metrics. And a lot of them will be derived off of these curves as well. So that kind of rounds out, so like, again, all that the code that you really need for performance metrics moving forward is kind of wrapped up here. And hopefully based on your understanding of like what precision is and recall is, it becomes pretty straightforward or like hopefully relatively intuitive to be able to interpret model performance based on the morphologies of these curves. And yeah, I have a few like takeaway messages beyond kind of really just listing what each of these things are as like a foreshadow to future testable materials. For example, if you're given a number of probability scores, can you basically trace out on an ROC curve like 2 or 3 points along that curve, right? So you would just like pick a threshold value. You would calculate your true positives, your false positives, your true negatives, your false negatives. You get your confusion matrix at a given point. And then you would have to measure out something like, well, you'd have to measure out your sensitivity and your specificity. And then based on those values, you know where on the ROC curve to kind of draw that out. It's like a nice question that kind of like cuts through the thread of all these different concepts. But really the like take home broader spectrum is that just to know that like metrics can be misleading. Again, if you have like class imbalance, your ROC curve and your accuracy might seem both really impressive, but that can be misleading because it's not actually potentially useful to the task that you want if you're dealing with like a very rare number of positive samples. Yeah, I'll like throw this out as a question just because I guess we have way more time. We have like 10 whole minutes. It's like 10 minutes more than we typically have, but I'll ask this, see if anyone has like an answer. So what does it mean when your model accuracy equals the proportion of the majority class? And hopefully that will inspire a little bit of thinking. So the idea here is your accuracy being the number of things you've gotten correct. Okay. Wait for a few more answers. Yeah, Chris Wang. So it predicts only the majority class. Exactly. So if you have 99.999 negative samples and just like 0.0001 positive samples, it becomes pretty clear that if your model gets 99.9999% of things correct, then all that your model has done is just predicted everything as negative, or as the majority class, in this case negative. So another kind of interesting question here, if the area under the ROC curve, sorry, this says greater than. I think what I want to say is less than and far less than. So if your area under the ROC curve is less than 50, do you have a useless model? And this might be a bit of like a, do you have a useless model? So Joseph says yes. Something I'll point out here. So in ROC space, yeah, so swap the two classes, exactly. Greg got it right. So it's like, if my model has this morphology, then I'm more or less correctly identifying, the class, each class as what it actually is. But if you mirrored this over this random line, so in fact, your ROC curve and the area under it was far less than negative, it just means that for some reason, it's with high confidence, it's saying all things that are positive are in fact negative and all things that are negative are in fact positive. So really, you actually do have a pretty good model. It's just mixing up those two. So all that you would do is take your predicted, okay, can you re-explain that? So here, if I have, so here, I'll draw from here. Here I have a model that gives a very low confidence value that it is in fact the positive class to things that are labeled 0. That's correct. And it gives a higher value, a higher probability that it is class 1 to the correct class. But if these colors were swapped, you would be assigning a very high probability to something that is class 0 and a very high probability to something that is class 1. So it's just confusing what those are. So if this is the probability that the sample is positive, this is correct. If we swap the colors and it's still, this is the probability that it's a 1, your ROC curve, instead of looking like this, would be mirrored over this line and would follow somewhere around here. Remember, random is right here in the middle. This is kind of the space you want to avoid. But if you have something that, is kind of, yeah, again, mirrored like along this curve, all you need to do is swap the labels. Yeah, exactly. Yeah, exactly, Kian. So that's actually the idea here. If you have something that's way less, your ROC is way less than 50, you actually have something good. Swap the labels, and now you actually have a very good model. You don't see that so often unless you make kind of like maybe a methodologic error or like a typo in perhaps your implementation. But if you ever see this, don't be disheartened. What you want to avoid is the 0.5. So yeah, I guess I'll like wrap up somewhat early-ish, unless anyone has any additional questions. I'd like encourage you all to go through the slides, like go back to the equations, and like play around with some of these. Like it's pretty easy, like I say, to measure different things. You can like play around with the logistic regression model itself. Like, I mean, this is like a very vanilla variant. So you can kind of like play around with different parameters on your model and see how that improves. Really, the key insight here is just understanding how your distribution of predictions will change. And if you can get, again, something where it's almost entirely predicted 0 in one case and entirely predicted 1 in the other, that starts to look like pretty good. I'd also suggest toying around with different types. So I add in here. So I add in here also the ability to the ability. I added code for a decision tree as well. So like a decision tree of like max depth 1, just as an example. I think this should all work. Yep. So a very, very simple tree will actually do this. So for a very simple tree, you end up with, unless you can pull out some actual value. So like it's like something is or is not the value, you don't have a good sense for generating some kind of confidence score or probability. Usually you can get that by considering several different types of trees. So if we were to increase, say, the max depth and allow it to be somewhat more complex, and we go through this process, you can actually see we do like pretty perfectly, right? We got zero errors. And then if we were to look at what that distribution of confidence scores is, it gets everything of the 0 class exactly right. It gets everything of the 1 class exactly right. So yeah, I'll encourage you guys all to play around with this. Without any other questions, I'll leave it at that. And yeah, if anyone has questions outside of this on some of the material, feel free to email me. Hopefully it will help clarify things. And yeah, good luck. Happy machine learning.